A crane is used to hoist a load of mass, we'll call it M1. The load is suspended by a cable from a hook of mass M2, as shown. The load is lifted upward at a constant acceleration of a meters per second squared. We're doing a symbolic problem here, so there are no numbers. I want to teach you how to handle the algebra. Determine the tension T1 in the lower cable and T2 in the upper cable as the system is accelerated upwards. Answer in terms of defined variables and universal constants. So, this being a dynamics problem where we are talking about tension, we are talking about acceleration, it's going to be a good idea to pick one of our objects, doesn't matter which right now, and draw a free body diagram and see what kind of net force information we can extract from that. Suppose we look at the lower box. If I were to consider all of the forces acting on this, I would have the force of gravity. We'll call it M1G. G, by the way, is one of the universal constants that we are allowed to use as a symbol. I must also talk about the force that is pulling this block up. The best we can do is call it T2. Now that's it. That's the only forces acting on this thing. Altogether, these sum up to make the net force. I would specify net force in the y direction. No need for that. Instead, I'll just say the net force on mass 1. And I'll take this red piece of information and I'll write an equation that we can get from that. The net force on M1 must be made up of T2 minus M1G. This goes with the convention that will say upward is the positive direction. This is why I have subtracted the force of gravity. The net force by definition can be substituted by Newton's second law with ma, specifically M1A. And if you think about it, looking at what we have here, M1 is a given constant, A is a given constant, T2 we'd like to find, M1G is a given constant, or rather M1 is a given constant, NG is a given constant too, or it's a universal constant, and we're allowed to use it. There is enough information here to solve for the variable of interest. All I have to do is isolate T2, which I will do by adding M1G to both sides. The result of this is that the tension 2 is equal to M1A plus M1G. In a nice compact form, I can factor out M1. I have M1, A plus G. This is one of our two final answers. But now we need to talk about T1, which we haven't even mentioned at all yet. We'll have to talk about a free body diagram operating on the object that actually is connected to this upper cable. Let's use another color to do that. If I talk about M2, then clearly I have T1 pulling me up. I also have M2G, the force of gravity on mass 2. But here's the thing. I also have, kind of stick it over here just to represent it, I also have T2 pulling me down. Tension is sort of bidirectional. I can say it pulls me in whatever direction it appears to be pulling, even though earlier I said that T2 was pulling me up from the perspective of the first mass. It's pulling me down from the perspective of the second mass and from the perspective of the hook. Now, consider all of these things that I have written and how they must sum up to the sum of forces on M2. And just like we did over here, let's write an equation that represents that. The net force on mass 2 must be equal to the positive T1 minus the things that are pulling me down, minus T2 minus M2G. Now, as usual, the net force, by definition, Newton's second law, can be replaced, substituted, with mass times acceleration, specifically M2A. M2A equals T1 minus T2 minus M2G. If I were to look at the things here that I know, I would know m2 was given acceleration. I do not know t1, I'm looking for it, but I do know t2. I've already found it, and it's already in terms of things that I'm allowed to report. m2, of course, I know, and g is a universal constant. The algebra will be to isolate t1, which we will do by adding t2 to both sides, and also adding m2g to both sides. Cancel, cancel. So, from here, we're going to report that t1 is equal to m2a plus m2g plus t2. Okay, but remember, t2 is something we know. Let's get more specific. t1 can be equal to m2a plus m2g plus t2, m1a plus g. Right? We said that was m1a plus g, just about out of space, but I think we're okay. So, altogether, in an equation I guess we could write in purple because it's sort of a combination of the red and the blue. We have that t1 is equal to, and I can do one more little simplification here. See these two terms, okay, by grouping, they both have an m2 in them, so I could factor that out. I have m2 a plus g plus m1 a plus g. And interestingly, again, if you want to be as compact as you possibly can, both of these terms, m2a plus g and m1a plus g, have a plus g in common, so I could factor that out. The best answer is a plus g, m2 plus m1. The tension in the first string. Naturally, the tension in the upper string is higher than the tension in the lower string. And both of these are higher than they would otherwise be if the system was at rest and there was no acceleration.